Hello, everyone. Thank you for tuning in today. My name is Ricardo Arias, and I am the manager of Dairy Specialty Products and Technical Support for United Animal Health. Today, I'm going to be talking about direct fed microbials and what I'm calling my attempt to demystify them so we can better understand what options we have out there and how to differentiate between the products that the market has to offer. Because guess what? Not all DFMs are created equal. I would like to start with current definitions for direct-fed microbials, probiotics, and prebiotics, and recognizing some of the differences between them. Then I'll review the different types of direct-fed microbials and their proposed modes of action, focusing on Bacillus-based DFMs and their functional properties, since that's our area of expertise, and the fastest growing segment of DFMs in the dairy industry in recent years. Finally, I will close with a brief summary of our findings in the field in terms of pathogen challenges in today's dairies and how to best approach those challenges. In the area of animal nutrition, the term direct-fed microbial was officially introduced in the US in 1989 by the FDA, and they defined them as products that allegedly contain live or viable microorganisms, it being bacteria and or yeast. So not much to go from there. But since the inception of that definition, there have been put in place strict regulations to ensure that these products actually have the microorganisms they claim to have in the amounts that they're supposed to be there, as well as providing evidence, supporting evidence of the benefits that they bring. The term probiotics, on the other hand, was not officially introduced until 2001 by a panel of experts from the Food and Agriculture Organization and of the United Nations and the World Health Organization, who defined them as live microorganisms which, when administered in adequate amounts, confer health benefits on the host. A definition that is accepted today around the world and actually conforms more to what we come to think of a DFM today. So these two terms are very similar and they are used interchangeably. Although the term DFM is still more commonly associated with products meant for ruminants, and the term probiotics is more associated with products meant for humans or other monogastrics. A more recent term is the term prebiotics, with an E. The term was introduced by Gibson and Rutherford in 1995, and they defined them as non-digestible food ingredients that beneficially affect the host by selectively stimulating the growth and or activity of one or a limited number of bacterial species already resident in the colony, and thus attempt to improve host health. So, these products do not need to contain live microbes, but rather a serious one or more compounds that stimulate the growth of beneficial microbes that already live in the host and provide a health benefit. Just like DFMs or probiotics. So ultimately the goal is to improve productivity or quality of life through improvements in gut health of all these products, on all these products. Here to the right, here's a list of microbials that have been reviewed and approved by the FDA to be used in DFM products. And as you probably could guess, DFMs have been around for centuries, but they have been more broadly used in cattle over the last 30 years. Initially, they focused on improvements in growth performance, milk production, or feed efficiency by positively altering the digestion in the rumen through modulation of ruminal acid production, promoting the establishment of desirable rumen microbial populations, or enhancing ruminal fiber digestion. More recently, with the advances in metagenomics, we have opened a completely new range of applications, more focused on the pharmaceutical field, in addition to the nutritional field. Currently, the application of probiotics and DFMs in ruminant productivity and health includes treatment of digestive disorders and reduction of gut pathogens, stabilization of the ruminal pH, enhance animal performance, increase feed conversion efficiency and fiber digestibility, improve milk yield and composition, stimulation of the immune system, treatment of mastitis, and methane production mitigation. We can classify direct-fed microbials in 4 kinds or types. The first one being rumen microbes, the second one being lactic acid producing bacteria, the third one being yeasts and fungi, and the last one being bacillus. Let's begin with rumen microbes. These DFMs are formulated with the same species of bacteria typically found in a rumen in large quantities and that are known to have beneficial effects in the rumen environment. Megasphaera, Selenomonas, and Propionibacterium species are lactic acid utilizing bacteria that have been used to enhance ruminal lactic acid metabolism. Prevotella species utilize starch but produce fermentation acids other than lactic acid. And Ruminococcus species are fibrillate bacteria that enhance fiber digestion. Since they are being introduced into their natural environment, we initially expected to be able to manipulate the rumen microbiome with these types of products. However, in controlled experiments, these microbes frequently fail to persist in the rumen when not fed daily. Being cultured in a lab environment, they may not have the ability to adapt and compete with endemic populations of microbes. They are also obligate anaerobes. This means they only grow in the absence of oxygen, which makes sense, as you would expect, since they are predominantly found in the rumen. And this may be the biggest hurdle in the development of these type of DFMs, since it complicates fermentation and viability in a commercial setting. Some of the proposed mechanisms in which it improves health in the animal are conversion of lactate to VFAs, production of propionic acid rather than lactic acid, increases in feed efficiency, decreases in methane production, and increase in ruminal pH. The second type are the lactic acid producing bacteria. The majority of DFMs used in cattle today contain at least one or more lactic acid producing bacteria with representative genera including Lactobacillus, Bifidobacterium, Streptococcus, Enterococcus, and Pediococcus. First introduced in cows only, these microbes have been administered to almost all classes of ruminant livestock. They are desirable as DFMs because they are easier to grow compared to ruminal microbes. They are environmentally robust and have a number of mechanisms in which they can alter or influence microbial communities. Some of the proposed mechanisms in the rumen are provision of a constant lactic acid supply, adaptation of overall microflora to the lactic acid accumulation, stimulation of lactate utilizing bacteria, stabilization of ruminal pH, and in the lower gut, they are known to produce antibacterial compounds as benzoic acid and bacteriocins. They can compete with pathogens for colonization of mucosa and/or for nutrients. They produce and/or stimulate the production and enzymes. And more importantly, they can reduce the pH with the production of lactic acid in the lower gut. And this discourages the growth of pathogenic bacteria. Our third type are yeasts and fungi. And yeast products have been extensively used and investigated in the dairy industry, especially because are high starch diets. They have a wide range of properties depending on the strain and are often fed to livestock as either live yeast, which is considered a direct fed microbial, a yeast cell wall, which can be considered a prebiotic, or a combination of the two. One of the major components of yeast and yeast cell wall products are polysaccharides such as alpha and beta glucans, and these polysaccharides not only interact directly with immune cells, but are also able to bind bacteria to prevent attachment and colonization of pathogens in the gastrointestinal tract. In addition to pathogen mitigation, yeast cell wall components may possess antioxidant and anti-tumor properties. From an animal health and immunity perspective, usable components from Saccharomyces cerevisiae have been reported to promote the release of cytokines from macrophages and may be involved with modulation of the immune cells in many species. Some of the other modes of action include reduction of oxygen in the rumen, as they are known oxygen scavengers, prevention of lactic acid in the rumen, that increases rumen pH, lactic acid being their main source of food, provision of growth factors such as organic acids and vitamin B. They can cause shifts in the rumen microbial populations, for example, an increase in fibrillate bacteria. They can improve ruminal end products, such as VFAs and ruminal microbial protein. And they can increase ruminal digestibility of organic matter. Our fourth type of DFMs are Bacillus-based DFMs. They are very diverse genus of rod-shaped gram-positive bacteria. Bacillus species are ubiquitous in environments all over the earth, including the gastrointestinal tract of most animals. One of their defining traits is the formation of endospores in the dormant phase of their life cycle. This endospore is extremely stable and stays viable throughout exposure to very harsh conditions. Another one of their superpowers is the ability to produce and secrete a wide variety of functional secondary metabolites. This is why they're used so often in the biotech industry and in various consumer products, and we'll see in a moment how this makes them especially useful as direct-fed microbials. Of course, not all Bacillus species are useful as DFMs. Currently, there are about 266 named species of Bacillus, with the number rising every year as the microbiology world sequences more genomes and subdivides the current species more specifically. Only 2 Bacillus species cause disease, and you can see them here on the right in the red cluster of the Bacillus family tree. You'll remember Bacillus anthracis as the microbe that causes anthrax. Its sister species, Bacillus cereus, is a minor source of foodborne illnesses. Many of the beneficial Bacillus species belong to the soil Bacillus group, highlighted with the green star, including Bacillus subtilis, Bacillus licheniformis, Bacillus pumilus, and Bacillus amyloliquefaciens. Along with Bacillus lentis and Bacillus coagulans, all these species are recognized as safe feed ingredients by the FDA and AAFCO and are widely used as direct-fed microbials. So what can they do? Well, first and foremost, they are able to produce endospores, which you can see stained in dark green in the first image. The endospore functions kind of like a seed during times of stress and allows the bacillus to survive extremes of heat, cold, radiation, and desiccation in natural conditions. In direct-fed microbial products, this gives them an extended shelf life and stability in hot, harsh storage conditions. Bacillus are also very good at secreting extracellular enzymes in large quantities. Some of these enzymes are commonly used in consumer products, such as laundry detergents and stain removers, and many of them are useful to us because they can improve the digestibility of feed and forage. These include lipases, which break down fats, exoproteases, which break down protein, and a diverse set of polysaccharases, which break down the indigestible fiber in feed and forage. They also produce a wide variety of antimicrobial compounds known as secondary metabolites, including antifungal compounds and antibacterial compounds that inhibit the growth of gram-negative bacteria like E. coli and Salmonella, plus gram-positive bacteria like Clostridium perfringens. Bacillus and the gut microbiome. Bacillus can have an influence on the gut microbiome from a few different angles. First, we have the antimicrobial activity we just discussed, which can directly impact the population of pathogenic or other opportunistic bacteria in the gut. Then we have the competitive exclusion principle, where DFM organisms compete for nutrients or take up binding sites on the mucosal surface that would otherwise be open to opportunistic bacteria. The opposite principle can be just as important. Bacillus DFM organisms have been shown to increase the population of commensal or beneficial bacteria, including important lactobacillus species in animal trials. This can be due to metabolite production, cell-to-cell signaling, changes in nutrient availability, or many other indirect effects. Bacillus effects on immune regulation can have an impact on both the gut microbiome and the host animal. Different strains and species of bacillus can have either a stimulating or a modulating effect on the animal's immune response. Immune stimulating bacteria can increase the host response to pathogenic gut bacteria, leading to a lowered population in the mucosal and intestinal wall. On the other hand, immune modulating bacteria can decrease the inflammatory response in certain chronic conditions, leading to a strengthened intestinal barrier and decreasing the damage of some chronic infections. Now I wanted to show you some of the results from our national surveillance for pathogens of U.S. dairies. In 2017, we swabbed cows all over the U.S. to determine the abundance of multiple pathogens and to quantify the toxin and virulence genes within these microorganisms. We asked key questions to determine which microorganisms and specifically which virulence genes were most abundant in sick cows compared to healthy cows. And we looked for patterns associated with dairy cow production stage and geography. Only understanding the complexity of microbial challenges facing today's herds can we have a good foundation for the development of DFM products that are efficacious. Our dairy surveillance revealed several key findings. First, we examined differences in microbial virulence genes quantities between healthy and sick cows, and we defined sick cows with recent clinical disease symptoms including diarrhea, HBS, DA, ketosis, and metritis as our sick cohort. And compare microbial pathogens and microbial toxin genes within those swabs to those of healthy cows in the same herd at approximately the same production stage. What we found was that there were not simply one or two virulence genes correlated to disease in these herds, but rather many. In fact, sick cows harbored higher quantities of toxin and virulence genes from E. coli, Clostridium perfringens, Clostridium difficile, Clostridium shavoi, and Salmonella species. And from a microbial ecological point of view, this actually makes sense. Many of these pathogens are opportunistic in nature, so when a gastrointestinal environment is compromised, these microorganisms can take advantage and proliferate, creating a situation that can snowball. To restore balance, a product must not be so specific that it impacts only one microbial, but rather have a broader coverage of opportunistic pathogens to be efficacious in shifting the balance of microbiota away from this stage of dysbiosis and back towards a healthy state. And I wanted to close with some final comments. While the potential of DFM products is high as prophylactic as well as therapeutic products, there are currently a number of technological, microbiological, and regulatory hurdles that slow down the developments in the field. But we are making progress as an industry, and I expect we will make great strides in the area of DFAs for ruminants in the next 10 years, just like we have in recent years with the human microbiome and the effects it has in every aspect of our metabolism. For Bacillus and yeast especially, but really for all the other DFMs, strains really matter. There are over 1,000 recorded strains of Bacillus subtilis alone. That's one species of all the bacillus that we discussed. And think about this. We have more in common with mice and chimpanzees as humans than some of these strains in the same species have amongst themselves. So strains do matter in these products. As with most things in our industry, one size does not fit all. Understanding the way these DFMs work will give us a better chance of picking a product that fits our needs. And just like every other product that is presented to us, it needs to pay for itself, and then some. Farm evaluations are the best way to measure some of the benefits we've talked about today. But for this, quality on-farm records are key and necessary. Finally, as antibiotic use continues to be restricted around the world for animal production, antimicrobial DFMs, gut health promoters, and immune upregulators become a viable strategy to keep our animals healthy as we switch from a culture of treatment to one of prevention. And with this, I want to thank you for attending this talk. And if you need more information, you can get on our website or contact me directly, and I'll be happy to chat with you. Thank you very much, and enjoy the rest of the conference.